All right. Hey, so let's do our first video walkthrough of the semester for ANCOVA, which I'm told is a bear of an assignment, but we're going to get you guys through this. So I have opened it, updated my license, which wasn't that hard. So the hypothesis here, this is a real study, by the way. So most of the ones we do this semester are people's real studies. This was a real master's thesis. And it's sort of a tale of what not to do. So let me take you on this lady's tale of the master's thesis that you don't want to do it this way. So her hypothesis, so remember she had trichotillomania folks, and her hypothesis was that folks who come from families who have trichotillomania are more likely to come from families that are less expressive. And she had other subscales she looked at as well of the family expressiveness scale. And this is why the write-up looked exactly like the one you wrote up, but that was a different subscale. I think that was cohesiveness or something. You're doing family expressiveness. So she thought they would be less able to express their feelings. That is a lower score on family expressiveness. So I wanted you to look at it a couple ways. First of all, the first way she did it, because it's just part of the story. So the first way she did it is she did an ANOVA. She did an ANOVA with just two groups, which you can do, even though normally that's t-test. You can do it with two groups. So let's go ahead and run an ANOVA. We're going to compare trichotillomania and undergraduate control group, because that's who her comparison group was, on their family expressiveness, and see what we get. So I have you do it in a slightly different spot so that you can do the ANOVA in the same menu. That's why we didn't use between subjects ANOVA the other way we did it. So we go to general linear model, we go to univariate. Our study group is our fixed factor. Family expressiveness is our dependent variable. Got to get a couple things. Number one is you got to go under e-means, and you got to take study group and put it under display means for. And it becomes important when this turns into an ANOVA, basically. That's why. Click continue. Then under options, we got to get our other things. That descriptive statistic gets our unadjusted means. Not that we have covariance yet. And then I'm no doubt ask you to get this. Do I do? Oh, yeah, of course. All right, that makes sense. And then finally, under plots, tell you to go ahead and put study group on the horizontal axis, click add, and I tell you to get bar chart, because it just kind of works better for this, I think. So continue, and that's it. Click OK. Come on, new version of SPSS, fancy. So here's our outputs. Let's just go through the questions one by one. So was the homogeneity of error variances assumption using alpha of 0.05? So was it violated? So let's go down to our Levine's test, and based on mean is the line we're supposed to use. That is not less than 0.05. So we have not violated the assumption. We have met the assumption. So was a homogeneity of variances assumption violated? No, is the simple answer there. But that's how you should have gotten it. I'm going to try to bold and highlight this stuff this semester to make it a little bit easier. So we got to fill in all this stuff in this table, and so let's do that. So test it between subjects effects. We need study group is right there. So 146.94 degrees of freedom for that is 1. So therefore our mean square, which I never told you is just degrees of freedom, sum of squares divided by degrees of freedom. So when you divide by 1, you get the same number. So it's also 146.94. Our F value is 22.29. And don't forget to put a little star on that. It is sig less than 0.05 right there. Right. And eta squared we'll do in a sec. Let's keep putting all this stuff in here. So error 580.04 degrees of freedom for error is 88. Our mean square is also the same thing, 6.59. So that's sum squares divided by degrees of freedom. So not the same number, but same process. So our total, so do either of these actually add up to the total? That would be 6,720. It does look like this corrected total adds up to the actual totals. But no, this semester, in fact, I'll just do it this way. Instead of sometimes they match, the best way to do it moving forward this whole semester is just calculate it. Just sum them up yourself, because there's times it works, times it doesn't work. So like the next table we do, it doesn't work. So 146.94 plus 580.04 is 726.98. That is what was here. This comes to 99, but whatevs, right? 726.98. And our degrees of freedom, I can do that in my head, 89. So to get our eta squared, to give you a little formula, it's the sum of squares for the IV divided by sum of squares for the corrected total. So it's the sum of squares there divided by 726.98 approximately. So let's do that. 146.94 divided by 726.98. Get 0.20 roughly, right? That's what I get. Hopefully that's what you got. So interpret the results of the Anova. All right, let's do it. So we didn't have to do Tukey because there's only two groups. So is there a difference in family expressiveness using alpha of 0.05? If so, look at the means and describe the differences. This is the what do you tell grandma thing. So this is what she originally got when she did her dissertation. So first of all, yes, there's a significant difference, right? P is less than 0.05. So look at the means. Who was higher? So you can either look at these descriptive means here, and the undergrads have a higher average than the trichotillomania group on family expressiveness. So the trichotillomania group, per her hypothesis, were less had lower family expressiveness, so they were less able, whatever the sentence says, less able to express positive and negative feelings about the family of origin. The person's not diagnosed with trichotillomania. So, I mean, one cheater way to do this is just copy this. This is exactly what you found, okay? Persons diagnosed with trichotillomania were less able to express positive and negative feelings about their family of origin than persons not diagnosed with trichotillomania, specifically her undergraduate comparison group. So I am totally going to cheat and put this in here because why not? And it actually worked for once. So persons. What? Oh, I see what's going on. Whatevs. 12 bold. There we go. So she was super excited when she did this, and so she was going in to defend her dissertation, and she found what she thought, not only for this subscale but for pretty much all the family subscales of the FES, that folks who have trichotillomania are came from families that were a little bit harder to deal with. So but what happened is when she went in for her dissertation, or excuse me, her master's thesis defense, someone on our committee said, hey, wait a minute. You compared trichotillomania tends to be among age 30 and older women. You compared them to a bunch of undergrad 20-ish year olds, I think, I'm guessing, from the psych pool, the student pool. What if the differences you got are just, you know, differences in age group or differences in gender? So they made her go back and actually see if age and gender were confounders of her study. So let's do it. So what are the two things that have to be true in order for a confounder to, or a variable to be a confounder? Well, it has to be related to the dependent variable, and it has to differ between the independent variable. So it has to differ between your groups. So that is a more complicated way of saying, were the trichotillomania group on average the same age as those who were undergrads? Were the trichotillomania group about the same gender distribution as the undergrads? That's really, that is the part where age and sex differ between the groups, those with trichotillomania or not. That's what you want to know. And the second part is that it doesn't matter if those things differ if they're not associated with the dependent variable. So you have to show for it to be a confounder that it not only does it differ between groups, but it's also associated with the dependent variable. Because if it's not, it can't, you know, it's not going to result in differences in your dependent variable, even if it does differ between the groups. So let's go ahead and give this a shot. So we're going to establish that with these right here. We're going to run the appropriate statistical procedures to determine if there's a statistically significant age difference between the study groups. And I just tell you, look, it's a t-test. So is there a significant age difference for the two groups? And if so, which group is older? Let's go ahead and do that. So compare means, NDT, and study groups are grouping variable. And how do I know what groups? So that is below the table here. 1 was trichotillomania, 2 was control. So that's how you know what your study groups are. So hopefully you put in 1 and 2 like that. And we want to compare average age between those with trichotillomania or not. So you stick age in that box. And that's it. That's going to give us our t-test. Look, you get effect sizes now. This is super fancy. So I'm going to click OK, and we're going to compare average age for those with and without trichotillomania in her study. Here's what we get, t-tests. We've seen this a lot. The average age of those with trichotillomania was 38. The average age of the undergrads was about half, 20, right? So is that just 1 or 2 extra Skittles? I don't know. Well, going down to our Levine's test, the first thing we note is that the Levine's test is less than 0.05. So what do we do when Levine's sig is less than 0.05? Well, we violated the homogeneity variances assumption. We got to drop a line. Equal variance is not assumed. So drop a line. I mean, it doesn't matter because the sigs are the same, right? Drop a line, we are doing two-tailed here, and either way, it's statistically significant. There's definitely a difference in average age of the trichotillomania and the undergrad. Specifically, trichotillomania, we're almost twice as old. Okay, not a problem. So let's say that. Is there a significant age difference? If so, yes. So let's say yes. The trichotillomania, I gotta spell this. Oops, what's it doing? What are you doing? Go away. There we go. Is it tricka or tricho? I have no idea how to spell this. Tricho. So when in doubt, just cut and paste, right? Yes, the trichotillomania group was, I mean, instead of saying twice as old, let's say they're about 18 years older on average, right? 18 years older on average. About 18 years older on average than those without trichotillomania. Okie dokes, doing good, I think. So let's bold all this and highlight all this so you guys can see stuff easier. So number 5, run the appropriate statistical procedures to determine if there's a statistically significant difference in the distribution of females in each of the groups using alpha 0.05. So we're going to look at the distribution of gender. So it says females because that's what she got accused of. Wait a minute, there's way more women in this group than that group. So that's why it's worded that way, but we're looking at gender. So we want to look at, I tell you it's chi-square test of it, it's all right. Put sex as the row variable and get column percent. Jesus, okay, I tell you exactly how to do it. I used to not. So this was one of those things I changed because so many people complained over time. So descriptives, crosstabs is where you get the chi-square test of independence. So I tell you specifically, put sex as the row variable. Cool. Study group as a column variable, I'm guessing. Which I don't say, but hey, hopefully you figured that out. We want to show that sex differs as a function of study group. And I tell you specifically, you want to get the column percentages. So that was nice of me. So I'm going to go under statistics, click chi-square. I will go under cells and I'm going to get what I said to get, which is column percentages. Cool, because they're going to match the AP right up. And I need adjusted standardized residuals. I think that's it. That's probably pretty good. Nope, I don't tell you to get a plot. You can get the plot, doesn't hurt. I'm not going to. All right, so here we go. Now we're looking at whether the distribution of gender is independent of study group, right? Which is an awful way of saying, is there a relationship between gender and which study group they're in? So let's see. So chi-square, first line, sig's less than 0.05. Oh yeah, there's a difference. That tells you it's statistically significant. Oh, I didn't get the V thing. Oh, Jesus. Was I supposed to get the V thing? Okay, one sec. Go back in, get the V thing. Kramer's fee is what I'm talking about. It might be in the write-up and I didn't get it. So statistics. Let's get Kramer's fee, run it. I love that it saves your old options. So you're like not screwed. You just pop back in there and add it, right? All right. So same thing, but now I got this thing, Kramer's fee. So 0.02, yeah, there's a difference in the sex distribution of the trichotillomania and non-trichotillomania groups. So let's take a look. So you can look at it, because it's dichotomous, you can look at it as a function of males, you can look at it as a function of females. I think females is a way to do it because that's what her committee was asking. So you're going to go to females and go, all right, and these are column percentages. So it adds to 100 by column. Each column adds to 100. That's why we got column percentages. Row percentages would be like this. So these would add to 100. So let's see. We've got 93.3% of the trichotillomania group was female. That was 42 out of the 45. 75.6% of the undergraduate group was female. That is 34 of 35. So the chi-square significance telling you these two numbers are definitely different. Okay, there's way more women in the trichotillomania group than the undergrad group. So okay, that's bad. So let's write that up here. There's a significant difference. The research group had a higher percentage of females. Yes. So yes. Can I still got it saved? Nice. Trichotillomania group had 93.3% females. Oops, not dollars females. Nope, not that either. There we go. Females. Gosh, new grade today compared to the undergrads with 75.6% females. So we have an age imbalance. We have a gender imbalance. Still not a big deal if these two things aren't actually associated with your dependent variable. So who cares if age differs? Who cares if sex distribution differs? If those things aren't associated with your family expressiveness, right? Doesn't matter. Hair length, for example, might differ, but because it's not associated with your family expressiveness, who cares? So that's what number 6 is. 6 is, are these two things also associated with your dependent variable? Because if so, we got a problem, Houston. So we're going to do correlations. We're just going to do everything, but I do tell you to do it in a specific order. Gosh, I can only imagine what story led to me giving this very specific instruction. So family expressiveness and age, and then sex, and finally study group. So our DV, 2 potential covariates, and then our IV. 1 or 2-tailed? Well, we're doing 2-tailed because we don't have specific hypotheses, right? We're just seeing, are these things associated? So boom. Does it appear that age and sex differences might explain our findings? Why would I say that instead of are they correlated? Well, because we've already established that they differ. So if indeed they're also associated with the DV, they can explain differences that she found in her findings. That's why I asked it that way here. So let's see, is age associated with family expressiveness? Yeah, so it's negative, it's statistically significant. So higher age, lower family expressiveness, right? One variable goes up, the other one tends to go down, statistically significant, it's got stars. So the older women, the older people tended to be less expressive, or come from families that were less expressive. All right, how about sex? It's kind of small, and it's not statistically significant, right? 0.08, not less than 0.05. So, so that is not significantly related to your family expressiveness, the sex distribution. So you'd say no relationship, no significant relationship between sex and family expressiveness. However, age is associated with family expressiveness, and it differs between the groups. This is a potential confounder. So I would say something like this. Definitely age could be a confounder that explains her differences. It's not her here. There we go. Differences, her effects, or what did I say? Findings. So that is the truth. So yeah, this happened to this poor lady. So, and so she's like, okay, so their potential or this is a potential confounder. Her committee asked her, even though sex was not significantly associated, it did differ, but even though it wasn't significantly associated with family expressiveness, this was kind of getting there. So they're like, put it in anyway as a covariate. And they do this to you a lot. Just be ready for it, okay? I guess I could have said sex less so, or that maybe not sex, something like that would have been fine too. I just didn't do it. So they then had her go back in and rerun what was an Anova by adding these two potential covariates. So it became ANCOVA, right? So the good news is you just go back in, because I had you do it under univariate. You just go back in. We're going to take age and sex, and we're going to pop them into the covariates box, not random factors. Click EM means, just make sure you, where is it? There we go. Make sure study group is still there. It is. That's cool. Options, still have the boxes checked for descriptors and homogeneity. They are cool. Let's run it. So now we're running an analysis of covariance. So here we go. So these means right here, those are those same means from before, right? Descriptives are the unadjusted or crude means. I don't want to skip to the end yet, but let's see what happened, you guys. So here you definitely got to add these things or it doesn't work. Okay. So let's fill out our sum of squares. I do give you the formula for the eta squared for everything. So let's go ahead and do this. So our age covariate, sum of squares, age is 19.36. What am I doing? 19.36 degrees of freedom is 1. So this is also 19.36. And so our F here is 2.99. Is that significant? Negatory, good buddy. It's not statistically significant. Weird. And that's like strangely similar to the correlation significance there, isn't it? But for sex. But nope, not statistically significant. I gotta sneeze, hold on. Well, okay. So take that, committee, right? How about sex? Was that so what does that mean, by the way? So because this wasn't significant, or do I ask that? Okay, I ask it, so I'll wait for a sec. So then sex 4.52. Degrees of freedom is 1. So again, 4.52. And our F for that, was that significant? No, it's tiny, 0.70. So very teeny tiny effect, definitely not significant. Neither of these get a star. Okay, so neither of those did much adjusting is what it means. How about study group? 17.62 degrees of freedom for that. Still 1. Mean square for that is still 17.62. F for that is 2.72. And is it significant? No, it's not. Wait a minute, it was before. So here it was, right? Here it was statistically significant. We threw in two potential confounders, right? And now we have a non-significant difference. The groups no longer differ on family expressiveness. Crazy. So I'll explain what the hell this all means in a sec, because yeah, this is like real life. So I guess one of the things about this semester is I try to give you these examples of real stuff that people ran into, because could be you. At least life is not just a bed of roses. It just isn't. So hopefully these help you this semester. So none of these add up to what you need, if I remember correctly. You just got to do it. So your total here is just something you got to calculate. So I said that in the lecture. So let's just do it. 19.36 plus 4.52 plus 17.62 plus 556.50. Really? An even 598? Okay. Seems wrong, but okay, 598.00. I'm totally adding that again because that's too weird. 19.36 plus 4.52 plus 17.62 plus 556.50. 598. I can do this one in my head. That's 89. All right, so eta squared is not the sum of squares for the IV divided by the sum of squares total here. It's sum of squares for the IV divided by the sum of error in the IV. Okay, so it's a two-stepper basically. We got to get the sum of these two things for the bottom here. So that's 17.62 plus 556.50. That's 574.12. I'm just going to write it down because it is a weekend. So 574.12. And we got to divide 17.62 by 574.12 to get our eta squared. So let's do that. 17.62. It's going to be something small. Divided by 574.12. I wrote 12. I hope that's right. Something small, 0.03. Hopefully that's what you got. Let me do it again because spending so much time talking. 17.62 divided by 574.12 is 0.03. Yep, that's our eta squared right here, 0.03. 3% of the variability. All right, using alpha of 0.05, do either of the covariates appear to account for a significant amount of variability in the expressiveness scores? Nope. And nope. No stars, not sig, not sig. So no. I mean, the short answer here is no. So it's funcal. Oh, I was gonna yellow everything. So let me go ahead and do this. Make your lives a little late, but could be worse. There we go. Bold. Okay. Short answer is no. It does not appear that either of the covariants accounted for a significant amount of variability in family expressiveness. They weren't significant. One of them was close. One of them was not very close, right? Close, not close. So no is the short answer. Do the study groups appear to significantly differ on family expressiveness after accounting for the covariates using alpha of 0.05? No, that is not less than 0.05. So again, no. Short answer. So we adjusted for two covariates, one of which was definitely a potential confounder. And something that used to, and neither of them accounted for a significant amount of variability, right, in the DV. Yet, nonetheless, when we do that, we find that our study groups no longer differ on the DV either. And this is the kind of crap that happens in real life when you do real research. You're like, well, anyway, this happened to this poor lady for real, and she was absolutely crestfallen. So, so this is, number 10, you're not expected to know the answer. I just wanted you to kind of think about, like, how do I not end up this lady? Okay. So the answer is something like this. How would you do this study differently if you're planning to do something similar for your dissertation? I think the answer is you need to ensure that the group you compare your sort of special group to isn't different in other ways, right? So remember, the goal of an experimental design was to have the two groups, if you can truly randomly assign, which you can't randomly assign to trichotillomania, but hang in there with me for a sec. Random assignment ensures that the two groups are as similar as possible on all other things except the independent variable, right? We can't do that here, but she picked undergrads who are very, very different from folks who have trichotillomania, who tend to be women above 30, right? And so I think the best way to do this is pick a better comparison group or more similar comparison group. If you're studying a group that's particularly different demographically, make sure who you're comparing them to is as similar as possible demographically to your treatment group or your group of interest. So I would say use a comparison group that is similar to your study group of interest as possible. That's not a sentence, but here's a good. That is as similar to study group of interest as is possible, I guess. So I mean, get a good comparison group, not a group that's really, really different because your particular group tends to differ dramatically from the general population, and in this case, in terms of age and sex. But it's like, you wouldn't want to compare a population of sociopaths to, fourth graders, right? Actually, that's a bad metaphor. So, but you get the point. Try to get to not end up like this poor lady. Really, this is a fault of the committee, right? She should have had people on her committee who are advising her and telling her that it's not appropriate to compare, who tends to be older women to a group of 20 somethings fresh out of high school. So anyway, hopefully you learn from her mistakes and this was useful for you, and I will get this posted. So check your work, because again, this semester I don't grade this. I read your APAs, but I don't grade this. So you might do go through here and make sure you correct your answers as well, so that when you get to the computational problem, you have a version where everything was done correctly and you know where to look. All right, I'm out.